Hello everyone, it's nice to see you all here. I am Mateusz and this is Blue, and we will be telling you about Ray on Golem here. I will start and Blue will come later to show you some live coding. We are, no, not coding actually, but running stuff on production. We come from Golem, and we are here today to tell you about Ray, which we believe is a very interesting tool for parallelizing and distributing your Python computations. While Golem is an open source project that tries to run sort of decentralized cloud, we are a very good fit for Ray, so that distributed Ray applications can run on our clusters for the benefit of everybody. Okay, so the plan is simple. Yeah? First, we will tell you that Ray is awesome. Then we'll tell you that Ray on Golem is awesome. And then we'll show a little bit this awesomeness. And we will wrap up with like a conclusion that basically we released MVP today. Just a happy coincidence. And it's an MVP, so it actually brings value to someone, but we have a long way to go. And we actually are looking for beta testers to help perfect it. And also, while Golem, Golem is interested in building like ecosystem around our product. And what we need for this is we need people who actually use Golem for something authentic and useful. And yeah, we are willing to support people who have some ideas how to use Golem. Okay, so let's move to Ray. First, what is Ray? Yeah, Ray is a framework for making your Python code run in a distributed manner. It is pretty nice in a way that big companies are using it, and it has in this AI wave, it is making big waves actually. So I wonder whether this wave reached Warsaw. So how many of you actually heard about Ray before? Okay, single hands. Okay, that's good. That's good because we have some interesting content for everybody. Okay, so basically what it does is runs Python code in parallel, which brings value also on a single computer because Python is single-threaded, and when you parallelize it, it can utilize all your computer's cores. So it is useful on one machine also, but it also is seamlessly can send the tasks to remote machines. So when you run out of your local threads, it can use this with machines that are far away from you. And this is all happening without changing any code. Yeah? So you develop your program locally with a subset of test data or something like that. And when you know it is working, you just push the computation to the remote computers to do a big heavy lifting. What is also very nice is that on top of Ray, there is a plethora of integrations and libraries that can be used to for the benefit of you as an application creator. That is just some logos. I know this one is the most popular, I think. This is the integration with Hugging Face transformers. Basically, the areas that you can use Ray is, like I said, general Python applications is one area. Generally data processing, use Python for data processing, and Ray can help scale this processing nicely. AI stuff like deep learning, reinforced learning, hyperparameter tuning, and model serving are the more specific areas that people use Ray for. Okay, what else? Okay, so to wrap up, Ray was designed for generic Python code, but now with the rise of AI and machine learning tools, it is being used mostly in those areas, which doesn't mean that it can't be used outside of machine learning and AI worlds. So this is roughly how Ray is built. In the middle, it has a library of simple building blocks that can be used to build a distributed program. And they are pretty simple. I will show them in a moment. They're pretty simple so that you don't have to be a distributed programming expert to actually write a code that runs on many processors. On top of it, you have there are 5 official AI libraries that can be used, and over this you have all those integrations I showed before. Underneath, you can run it on single computer. You can run it on a couple of computers that you manually connect into a cluster, or you can run on a Kubernetes or any public cloud, which is also nice. Okay. So let's go to the building blocks of Ray. First mechanism that you can use with Ray is remote tasks. You can imagine a function that returns some result, and imagine that you want to run it a lot of times. So this code will run the function sequentially, right? With Ray, it can look like that. You decorate the function with Ray remote to tell Ray that this piece of code can be run on a remote computer, on a remote worker. And then instead of calling the function directly, you call it like this. And instead of getting a result straight away, you get a future that later can be awaited on with ray.get. So basically what is happening here is that Ray schedules 1,000 of tasks to be executed somewhere, and internally the tasks end up in a queue. Ray schedules the tasks on available workers, but when the queues are getting bigger, it tries to increase the size of the cluster. So it can request new nodes to be added to the cluster. And then when the new nodes are added, they get new tasks, and the queues are getting empty. And eventually, when the nodes are idling, because there's no more tasks, Ray notices it and brings the nodes down. So this way, it's called Ray autoscaler, takes care of the size of the cluster. Yeah? So it can increase it to speed up the computation, and it can decrease the size of the cluster to save you money. Okay, so this is simple remote tasks. This is the same code. Instead of waiting for all the futures, like here you have 1,000 futures that we can wait for, we can use Ray wait to await an arbitrary number of the futures to be returned. Yeah. Another building block Ray uses is actor, and actor is like a stateful worker. So basically, you decorate a class to make it into a Ray actor, and when you instantiate this object, Ray creates a separate process that preserves the state, and then when you call the methods, it makes sure that no method are executed at the same time. Yeah, so basically, this actor has one big mutex, and this mutex protects the state of this of this object. And finally, we have remote objects. You can put an object to array local storage. The storage is local to the worker that executed the put, and then from wherever else you can get the object. If this is happening from a worker that doesn't have this object in the store, array transfers, copies actually the object to the local storage of the worker that executed the get. Yeah, the objects are immutable, but you see that this can work easily. Okay, so these are the building blocks. What we have here. Yeah, so basically this is Ray. You can use all those mechanisms to build program, and Blue will be showing some of those in a moment. Yeah. So this is why we believe that Ray is awesome, because actually what I like about this is that actually those mechanisms are pretty easy. And then Ray takes care of very many details that happen underneath. Okay, so we were supposed to have a part 1 of demo, but we decided to drop the part 1. So let's move further. Now let's move to Golem. Let's move to Golem. Another question for you: how many of you know about Golem? Oh, some more than Ray. Nice. Cool. Wonderful. So there is a very popular term recently that nicely describes Golem. This is decentralized physical infrastructure network, which basically means that Golem is like a place where people trade, share computing resources. We are an open source project, and we have two users in our two users. One kind of user is in need of computing power, and they can rent this computing power from the other kind of user, which is providers. Yeah, so basically providers put input computers into Golem network, and requesters can run stuff on their computers. So basically like a marketplace. Golem is matching to needs. We are building it in a way that is decentralized, which means that it is that there is no central entity that controls this network, which basically means that if you're running something on Golem, nobody can stop it, which is a nice feature. The payments between the requesters and providers are made on the blockchain, but you don't have to interact with the crypto yourself. You just need to top up the account at the beginning, and then it happens by itself. Which is interesting also, that we as the Golem doesn't have any earning in this, any profit, because everything that the requester pays goes directly to the provider. Yeah? So Golem is interested in building this ecosystem of people sharing resources, and this is our main mission. We are supporting CPUs and GPUs coming soon. Actually, the example we will be showing you is based on a GPU, actually a couple of GPUs. But in our network currently, we have like 800 providers with about 2,000 CPU cores. Yeah, this is nice power. As this is a small caveat that I'd like to disarm before it blows. This is a community-powered network. Yeah? So basically, in terms of data privacy and node reliability, you need to know that this is a community-based network, right? Okay, so this is about Golem. Where it fits on this, where we fit on this screen, we are here. Yeah? Instead of running Ray application on Kubernetes cluster or Amazon cluster, you can run it on Golem, and which makes Ray Ray on Golem, a cluster provider for Ray. Yeah, Ray has a very nice interface for implementing cluster providers, and there is plenty of community-based cluster providers in Ray repositories. And Ray on Golem is one of them. And basically what we aim for is easiness of use. Yeah, so what we want to achieve is that when you are ready with your Ray application, it should be super easy for you to run your code on Golem. So you need to do 4 things. You need to install our package. Then you need to download a configuration file. Then you can start the cluster. The configuration file contains definition of a small cluster that is running on our free test network. So you can see that it is working. And then, so this is it. And then when the cluster is up, you can submit your Ray application to the cluster and it executes. This is like our holy grail, that this looks like that and easy and fast. It is true only for Ray applications that don't need too much requirements. Yeah? Inside the images that we start on our providers, there is only vanilla Python, and if your application needs anything, you need to edit the configuration file to tell it. Actually, this is the place when we might be using UV, if I understood correctly, because downloading the packages can take too much time of our providers. Okay, so this is the idea. Thanks to running this on Ray, we get auto scaling, which helps you to increase the cluster when you need power and downscale the cluster when you want to save costs. When we compare Golem and public clouds, we don't require any signups. We don't need an account setup. We don't need to discuss with infrastructure department to configure anything for nothing. Yeah? It just works. We provide you with a free test network, as I said before. The computers that are not very powerful, but they are enough to see that the scaling works and everything. The switching to the main network is fairly easy. You need to change one line in the configuration file and top up the account. But basically we aim for easiness of spin up and cluster management. I think this is now the time for you, Blue.
Is this on? Okay. So I'm gonna reintroduce myself. My name is Przemysław Idzkiewicz, or Blue Shade for the simpler version. And contrary to what was said in the introduction, my name is just Idzkiewicz, not Idzkiewicz, without the Polish character in the surname. Anyway, so what I'm going to show you is just what Mateusz has mentioned earlier. So I made a simple POC of using stable diffusion on Ray, just to prove that it can. So I already have the repository downloaded. So I'm going to just spin up the cluster. So this is what Mateusz said. This is Ray up. It's going to take probably a bit. It shouldn't take too much. So we're going to stay here. Okay, I'm going to switch to the code, and we're going to come back here for in a few seconds. So as Mateusz mentioned, there are those mechanisms that allow you to connect to Ray. And so this is the actor class. This is the stuff that executes on remote machines. And as you can see, I used actor because there is a model initialization going on underneath. And it needs, loads the whole model, which is several gigabytes. And the model is actually stored on the image, which is deployed on the providers. Oh, as you can see, it's not going too well. This is why we only want to spawn the model once, and then like render the images based on the prompt as many times as we wish. So Mateusz, what do we do? Do we show the recording or do we wait longer? Because I'm not sure whether it's gonna spawn here. I'm gonna stop it and just restart it.
Yeah, as I said, GPUs are still in beta.
I mean, the thing is that we just have a few machines right now spin up on our test network, and it's a pretty fragile configuration just for the moment, because were we to use CPU providers, there are like quite plenty of them on the network, but we chose to use GPU just to show that there's something interesting that you can do on Golem. Just the thing is that right now, yeah, the machines are just 4 of them, and sometimes it takes quite a long for them to see each other in the network and to be able to connect. We just tested it before, but as you like an right now it just spun up quickly. The old rule for the presentation is that it stops working the moment you start the presentation. So there we go. Anyway, I will return to the explanation of the code in a second. Yeah, I'll just do one thing. Because it spawns just the head node, Ray head node, like the node that's controlling the cluster. But we also want to have a couple of workers in there. So I'm going to attach. As you can see, that's a pretty convenient mechanism where you just give it the YAML configuration YAML, the file, and it just connects to the head node with SSH underneath, and you can execute already stuff on the provider node. I'm gonna launch. So this is the state of our machine. We have one GPU for a moment, and we want to have like at least 2 of them. So I'm gonna hopefully wait, and hopefully it will spin up another one. If not, I will run the demo with 1 GPU, but it won't be as effective as with a couple of others. But in the meantime, I'm gonna finish explaining what we have here. So as I said, we keep the state in the actor because we only want the model to be spawned as little times as possible. So if we have like 3 GPUs, then the model is initialized once on each GPU, and then let's skip the argument parsing part. So then we spawn those renderers, I mean the actor class, the instances, and with that we have a small loop that just calls this is the code that actually calls this render image method on the actor, and we use array weight to get like the first result from the first actor that gets it, and we then schedule another image from the same. So we have 2 GPUs already. So yeah, I'm not gonna wait any longer. So yeah, we can detach from the machine, and right now we use ray submit command to give it some work to do. And I'm gonna need a prompt from you. Does anybody have an idea for a prompt? Yeah. Okay, typical Polish person drinking beer. Yeah. And we were gonna render like 16 images, maybe. So yeah, that should do it. So right now it sends the script for execution, and it's gonna spin to 2 workers. As you can see, 2 available GPUs and 16 images to render. So it spins up the model on 2 GPUs, and then right now it generates the images. There is a lot of like this repeated cluster, repeated message across the cluster, because Ray tries to deduplicate the communications for you, so not everything makes it into this console. As you can see, the subsequent images are generated independently on each of the worker nodes. So yeah, I'm gonna just wait. It shouldn't take too long. And these, for context, these are like 3060 NVIDIA machines. So not the top of the league, but pretty strong anyway. And we have already, I think, like more than, I don't know how many, like 20 machines or 20 like on the beta testnet.
Yeah, 20 in the testnet, and I think 20 beta testing on the mainnet.
So if you wish to use Golem mainnet, then you could use like production machines that actual people on the network make available for you to use. We are using our own machines that we just spin up in the office just to be sure that they are there and they are not taken by any other work. So as you can see, it's close to finishing its work. It's scheduled the last image for execution. And all the images end up on the head node. So we have just 2 workers. So the other one has to download the final images, but they are already here if it's finished. And I'm gonna just sync them down. So right now we are just downloading those small files from the head node. So yeah, they are here. Or they should be here. Typical Polish person drinking beer. That's gonna be interesting. So what the hell? Yeah, that's cool. I like it. Yeah. So what we did is just we yeah, what we distributed was, of course, generation of the whole images, not like parts of single image. Oh, which one? Oh, this one, yeah. Okay, I like this. Yeah, that was a really good prompt. Thank you. So yeah, this is pretty much end of the demo. I'm just gonna spin down the cluster so it doesn't make the machines more busy than they should be. So yeah, this is end of the demo. So I'm gonna pass voice back to Mateusz.
Yeah, thank you. That's a very good prompt, actually. So what you saw here is that Ray can easily distribute work across different nodes. The Ray and Golem can actually hold them. What you didn't see is that that there is many of nodes on Golem network. Right? we chose to see the stable diffusion because this is sexy and cool. But last week we have run 2-hour-long computation with 50 nodes, like throughout the time, with 600 CPUs. Yeah, so basically this is working, and we are very proud of it. To sum up, what we get from Ray, we get the code that is parallel and it can run faster thanks to that. We get the seamless expansion of our local machine to the hundreds of remote machines. And we got a simple and straightforward model that allows you to develop distributed code, even though you are not don't have to be a distributed programming expert. From Golem, on the other hand, we have the easiness of the configuration and very straightforward cluster management. And we didn't see this, but we had put some work into controlling the expenses of the cluster, and this is also something that we believe Ray and Golem should give you. So if you are new to Ray, what Ray can give you is that Ray can extend your local machine to use a big cluster of remote machines, thanks to the autoscaler that is happening behind the scenes underneath. And Ray itself offers a very big library of examples that you can take inspiration from. If you know Ray already and you use it, then Ray on Golem tries to be a little bit less hassle-full when scaling, in terms of scaling. We aim for simpler setup than our competition. And basically, it's another backend for Ray applications. Okay, so this is literally the last slide. I hope you saw and you believe now that Ray is actually very nice. That Ray on Golem can be useful to running Ray applications. And for us, as I told you before, yeah, for us, we are on the beginning of the journey. We need people who could help us bring it forward, make it better and more production use. So if you find this interesting, just reach out to us. There is a couple of us right today in the audience, and you are free to talk to us now or later. Here you can go to sign up for our beta tests, and here you can sign up for individual demo that we can and discussion about Ray. Okay, I think that's it. Do we have any questions?
So first of all, thanks for the talk. How does Ray compare to Dask, or can you run Dask on Golem?
What do you mean, task?
Dask, D-A-S-K.
Okay. So I'm not aware of the tools.
This is also a library for distributed computing and distributed machine learning.
So I would say that what we are integrating is just right now Golem became a backend specifically for Ray. So if you use Ray, you can use our node provider configuration that just makes Golem available as a backend for Ray. But if you wanted to use it for Dask, probably you would have to do the same for Dask. So
I see.
but it should be straightforward if it provides such an app.
I'm not sure, but I think that this is Dask logo. so I'm pretty sure the Ray somehow integrates with Dask.
Regarding the computational power providers, have you considered the usage for professional uses, like commercial uses, where you have to keep your data in a given region, for example, that you cannot send data outside of European Union? Do you have a service or a mechanism to secure for that?
Well, Golem itself is not prepared to handle like secure data because it all runs on provider machines, and providers can access this whatever the provider has access to. You can override the execution environment with your own, which just downloads, for example, the files, even if you treat it as a secure. But if you wished to use Golem in such an environment, you could have your own cloud of providers created in some data center, and they could use a different subnet, and they could use their own relay to connect, and then you would be sure that you're using them. But yeah, this is like a specific setup. You could use it. Just it's not regular Golem network.
Having said that, I think that there is some information about providers in our network, and if you dig down, you could also select providers that have IP from a selected region, if the region is the only thing you need.
As I can guess, you can use the different CPU architecture, right? So it can be like it works as well as on x86-64 and on ARM-64, right?
I mean, you're
So-
asking about providers or about?
No, I'm asking about CPU architecture. Like, is it transparent regarding what kind of CPU is in the backend?
I mean, if you want to run Golem provider node, so you want to make your hardware available in Golem network, as far as I remember, we only support x86 architecture at the moment. But if you want to use Golem as a requester, as a person who needs to use computation of other machines, then you can use any other architecture, because it's like the client is pretty thin and it's not resource heavy, and we have binaries to run the daemon on ARM, and we have daemon for any other, like Mac OS or Windows. Just for the provider part, right now it only works, at least this runtime that we use, it only runs on x86. Yeah.
Okay, so it should run on ARM, but it's not tested, right?
Yeah. If you
This is the status, right?
yeah, it's not. It's right now it doesn't support ARM, but we could make an execution environment available on ARM if there were so many providers wanting to run their providers on ARM.
Okay, thank you.
So once again me. So let's say I want to use Golem and I need some additional computation power. Can you tell us what do I need to do step by step to actually use it? I have a script right now, ML based.
Okay, so I mean, there is a caveat, as there are. I mean, if you wanted to use Ray on Golem, it's basically what Mateusz showed, that you just install the dependencies and then you just spin up the cluster based on some constraints, and then you just submit the script. But there is a caveat, because what we give you is like a plain Python with some basic libraries and like one version of Python, and that's it. So if you need like more dependencies than that, you need to install them, which can be done, just it takes time. And what I did with this Stable Diffusion POC, I prepared the image, because you choose when you create this cluster description file, you provide the image, like a Docker-like image that's deployed on the nodes. So if you want, you can write a Docker file that contains all the tools that you have, then build this Docker file to the Golem image and deploy this image on the network, and then it will contain all the tools. So if you have this image, then you can spin your nodes and they will use the image, so it's going to be easy.
Yeah, the payments are happening on the blockchain. So if you are going for the mainnet, you need to top up the wallet that is hidden inside Ray on Golem, and we provide a simple onboarding portal that allows you to buy some crypto with your credit card, and then you can use those tokens to buy computing power from the providers.
So I'm someone who's maybe a little bit ignorant of this distributed execution landscape. But I'm maybe not the only one in this position here. So I'm going to ask, who's behind the Golem project itself? And like, what's the relation between Ray and Golem as a project that you've got in your shirts, which are pretty cool, and Golem itself, which I suppose is a more generalized platform that more people use?
Okay, so basically Ray and Golem are two separate open source projects. Ray is developed by a company that is named Anyscale, and but it's open source and everybody can contribute to it. They earn their money by providing like a layer above Ray that allows you to manage, it gives you an interface to manage your Ray clusters, and this is how they make money. And Golem is a project that has been whose mission is to match make the people who want to share their computing power with people who want to get computing power. We got crowdfunded some time ago, and hence we have the funds to do it. We don't have to earn anything on the Golem network, and we are interested in making and fulfilling the ideas that we got the funds by encouraging people to actually use Golem, so that the providers can actually get paid for their computing power. This is the Golem's mission.
So I'm going to follow up just with the latter part of your question. So Ray on Golem is just a team of people working for Golem inside the Golem team, and we are just responsible for building this this integration of Golem with the Ray front end. So that's basically what Ray on Golem is.
So once again me, and so how do you look like from the perspective of price per CPU hour in comparison with GCP or AWS? Are you considerably cheaper, or what's your benefit?
Yeah, this is a tough question because it's not very easy to compare. But we believe we are very much cheaper, but we don't have data to prove it now. Yeah, so when I told you about this computation that it took 2 hours, we were using like at average 40 to 45 computers with average 500 to 600 CPUs, and we paid 30 cents for 2 hours of computations. But to be fair, the computations were doing sleep, so they weren't using much CPU, and our providers charged for the CPU. So.
I would be very much interested in how the GPU usage influences the spendings, but I wasn't yet able to use it on the mainnet because we only have like just started the beta program for the GPU providers. So yeah, we didn't yet.
Our GPU team estimates that it should be like between 4 and 10 times cheaper than GCP. But there's one more thing that we don't have. We have consumer GPUs, right? We don't have big GPUs because there are regular people who contribute their hardware.
Thank you.